Good evening, everyone. My name is Franny Mace, and I am an undergraduate TA for Introductory Astronomy at UNL. I wanted to welcome all of you to the 2022 Ruckman presentation. The Jerry E. Ruckman Lecture Series is sponsored by the UNL Department of Physics and Astronomy and made possible by the generous endowment of 1962 UNL Bachelor of Science Physics major Jerry Ruckman. Each fall, we host a nationally recognized educator speaking on popular science topics or physics education issues. Our guest tonight is Dr. Michael Lamb of the Rochester Institute of Technology. Dr. Lamb did his undergrad work at the Colgate University and his graduate work at Cornell. He is a member of the North American Nanohertz Observatory for Gravitational Waves, whose goal is to detect and characterize low-frequency gravitational waves coming from a variety of sources, such as supermassive black hole binaries at the center of merging galaxies. His talk tonight is titled Celestial Clocks and Ripples in Spacetime. Please welcome Dr. Lamb.
Okay, thank you everyone for coming. As said, I'm Dr. Michael Lamb. I'm a professor at the Rochester Institute of Technology, and I've been a member of the North American Nanohertz Observatory for Gravitational Waves, which I know is a mouthful, but in a few minutes you'll all understand what that means. I've been a member with Nanograph for many, many years now, and I want to tell you about the work we're trying to do opening a new window into the universe, into the gravitational wave universe. If you were to go out and look at the night sky in a relatively dark location, this is something that you would observe if you had really, really, really good eyes or a pretty good camera setup. You see all of the different stars in the background. You can see the Milky Way. That's the plane of our galaxy, the galaxy that we're in. You can see that there's dust blocking and obscuring the light from behind, from stars really, really distant. This is what the universe looks like in optical light that we can see with our eyes. And if our eyes were actually tuned to radio waves, which are another form of electromagnetic light, this is what the universe would look like. You can see it looks a bit different. There's still lots of dots. There are these wisps and bubbles going around. But one really important thing to note that each one of these dots in this image is not a star. Each one of these dots in this image is an object called a quasar, which comes from a supermassive black hole billions of light years away from us. And so that means that when we look at the universe with radio eyes, we see a very different picture of the universe than we do when we look in optical eyes. And this has been characterized greatly as of late with the James Webb Space Telescope, which is an infrared telescope. It's the successor to Hubble, which is an optical telescope with a little bit of infrared and UV capabilities. When we combine measurements from across the electromagnetic spectrum, and so what you're seeing here is a false color image of Stephan's quintet in infrared, in optical and X-ray, we see lots of different physical processes that are happening, more than we would have seen if we were just looking in optical light. We can see gas flowing between these merging galaxies here. We can see shock waves that are moving through. The universe looks very, very, very different. And indeed, if we look at just our Milky Way across the electromagnetic spectrum, so the very top here are the lowest frequency, the longest wavelength electromagnetic waves, radio waves. We can move down across the electromagnetic spectrum. We have the infrared here, moving down into the optical, which is what we saw in the first slide, and then even into the X-ray and the gamma ray. Again, the universe looks very different. There's different physical processes that are going on that cause these different emission mechanisms. So astronomers for a long time have wanted to build telescopes across the electromagnetic spectrum so we can get an understanding of what is going on in our universe. And every time we build a telescope and open up a new window in the electromagnetic regime, we learn lots of things about the universe that we didn't know existed because we couldn't observe them before. Every single time this has happened. And in 2015, LIGO and Virgo made a really, really, really big step forward in our opening of the windows to the universe, where they did not observe electromagnetic waves coming from a source. They observed gravitational waves. That is the actual bending of space. I'm going to get into more of how gravitational waves affect space, the space that you and I live in right now. But they made this very, very, very incredible discovery back in 2015, and since then have been prolific. They have seen many, many, many more of these gravitational wave events that you cannot see in electromagnetic light. So they've opened up an entirely new window to the universe, one of which is equivalent to one of these electromagnetic wavelength ranges. And so what we want to do, and what I want to convince you of tonight, is that not only are LIGO and Virgo detecting gravitational waves, but that there's gravitational waves of all different wavelengths, just like there are electromagnetic waves of all different wavelengths. And we can learn new physics from opening up each one of those windows. LIGO has taken the first step, and my collaboration Nanograv, we hope to very soon take the second step. And so this is a cartoon of the gravitational wave spectrum and the 4 different types of observatories, or 4 different types of detectors that people are trying to build or have built to detect gravitational waves. And on the bottom axis here, I have the frequency of the wave, so how fast it's rippling, or going this way, how long it takes for one of these waves to ripple around. And so ground-based interferometers like LIGO and Virgo, they sit at the very high frequency range, where they're observing objects that are spinning around hundreds of times a second. And they're emitting gravitational waves with periods of fractions of a second, moving really, 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 really rapidly. So they've done an amazing job. My experiment lives all the way down here with what are called pulsar timing arrays. And we're going to get into what a pulsar timing array is very, very shortly, where the frequency range is down at about 10 to the minus 9 hertz. That is 1 nanohertz. And that's not a very usual unit. So for reference, 1 nanohertz is equivalent to a period of about 30 years. So my experiment, instead of looking at things merging and producing gravitational waves that are cycling very, 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 very quickly, we're trying to detect waves with periods of weeks, months, years, and decades. It is a much more long-lived experiment in all of this. And you have to imagine that the sources that produce those gravitational waves have to be different from the sources that produce waves that are happening very, 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 very fast. This axis here is what's called the strain, and I'm going to get into that in a little bit. That represents the strength of gravitational waves. And I'll go into just how incredibly small, how incredibly weak these gravitational waves are. Okay, so first thing when talking about gravitational waves, we have to crash course on is, what does general relativity say? Einstein is a very famous person, very smart guy, who 105 years ago, 107 years ago, came up with general relativity, which describes how space and time work in the presence of things like mass. And there's not going to be any equations in this, so don't worry. But if there was nothing in space, if there was no objects in space, space-time might look something sort of like this. This is what we call flat space-time, where if you take a little tiny particle and it moves along, it would move along in a straight line unimpeded forever and ever and ever. But the second that we put a mass in the center, that causes all of the lines around it to warp and bend towards that source of gravity. And the stronger the mass is, what Einstein predicted is the stronger the warping of space-time. This is what causes things to orbit. So if you have the moon orbiting around the Earth, or so you put a satellite in orbit, it is moving around in this curved space-time. That's what Einstein described, and we have yet to find where he is wrong in his description of how gravity works in our universe. And so gravitational waves are what happens when you take among other things, two objects, have them orbit around each other, and you have to, in your brains, imagine, because this is incredibly hard to picture, but you have to imagine that both of the objects are warping space-time, and they're warping space-time extremely, but far away from the objects. As you get this warping, you'll get these ripples that propagate out. Just like if you were to take two fingers in a pond and you were supposed to cycle them around, you would get ripples that propagated outwards. And those ripples are going to cause changes in space-time that we can observe here on the Earth. LIGO and Virgo have done so many times now successfully, and we're trying to open up the search for gravitational waves at other wavelengths. This is a really crude picture. You have to imagine that space-time is a four-dimensional thing, 3 dimensions of space, 1 in time. That's really hard to picture on a 2-dimensional graph here. Maybe it looks something a little bit more like this, but it's really hard to visualize. There's no easy way of doing this. The effects of gravitational waves are actually fairly easy to understand, though. If a gravitational wave was passing through this screen right now, right at you towards the audience, if I took a ring of particles and I put them in a circle, over time, they would stretch and compress in one direction. So maybe you would have a ring of particles like up here. They would stretch and compress up, go back to being a circle, then stretch and compress in the other direction, and then go back here. And so what's the effect is that if a gravitational wave is passing towards you, the distances between these particles is changing. The actual physical distance in space is changing. And we call the strength, of gravitational waves the strain, which is just fractionally speaking, how much are these particles changing in size? And this is an enormous strain, this fractional distance here. For an experiment like LIGO, their first whopping big detection was a fractional change in distance of 10 to the minus 21. So well, actually, I should say 21 zeros and then a 1. Okay, so it's an incredibly tiny deviation in the circle that they were able to detect. My experiment has the advantage of trying to detect gravitational waves that are 1,000,000 times stronger. So we only need to detect things with 10 to the minus 15, which is still an incredibly tiny number. But we have that advantage. And so what we need in order to detect gravitational waves is some measure of the distances changing between 2 points. The way that we do this in a pulsar timing array is to say that if space between 2 points gets stretched, so there's more space between those 2 points, we can use the speed of light as a ruler because the speed of light in a vacuum is constant. If there's more distance between two objects, it takes light longer to go from one object to the other. And then if the space gets squeezed, it takes light less time. So what we're looking for in space is some kind of mechanism by which we can measure light and use it as a clock. Measure when, for example, some pulse will arrive at our telescope either early or late. And that's where these objects pulsars come in. And if you take my introductory astronomy class, you learn all about the life cycle of stars, and I don't have time to get into all the life cycle details here. For a star like the sun, which is a pretty average type star, it will live through its life for maybe 10 billion years, and it will burn hydrogen into helium. And later on in its life, it will shuffle off its outer layers, puff that off into these beautiful nebula, and leave behind an object that's just the very remnant core, and we call those white dwarfs. And the vast majority of stars in our universe will undergo that process. They will end up shuffling off their outer layers and ending up dying and leaving behind this dead remnant object. If a star, on the other hand, is extremely massive, its end of life is much more violent. It can leave behind in a giant supernova explosion a core which is so massive that gravity pulls everything in towards the center. And that's an object called a black hole. That's an object where gravity is so extreme, it wins against any possible other force, and everything gets pulled towards the center. In between those two, a white dwarf and a black hole, when you have a very massive star, but not quite as massive, you get an object called a neutron star. And a neutron star is essentially a giant ball of neutrons. It has some of the most extreme physics in the universe. I'll get into some of those right now. Neutron stars typically have about the mass of the sun, so 1 to 2 times the mass of the sun. But you take that and compress it into a size of about a ball of diameter, maybe 24 kilometers, maybe 20 miles or something like that. 15 miles, actually. So here it is superimposed right over Lincoln. So you take the entire mass of the sun and squeeze it right over Lincoln. And that's one of the most extreme objects in the universe. They have densities that are higher than that inside of the nucleus of an atom. 1 little teaspoon of it weighs as much as like the Great Pyramids. Okay, so just a little teaspoon of it is just incredibly, incredibly massive. Okay, so the densest objects in the universe. And neutron stars, because of the way that the stars before they underwent a supernova explosion were spinning around, they end up spinning very, very, very fast. The fastest spinning ones can spin hundreds of times a second. So now you have to imagine something the mass of the sun over Lincoln spinning as fast as a blender. Okay, and we know of many of these objects. I observe lots of them all of the time. And these neutron stars, many of them are called pulsars because they look like they pulse. They send pulses at us, and that's totally an effect of how the emission is coming across our line of sight. They act like cosmic lighthouses, where if you have the beam of a lighthouse passing you, you don't see anything, and then the lighthouse gets bright, and then you don't see anything, and then it gets bright again. So these pulsars are not physically pulsating. They're not getting bigger or smaller or doing anything like that. They have these beams that are coming offset from their rotation axes, and it's just an effect that as they spin around, we see them pulse. On the side here is a strip chart reading of the first discovery of a pulsar by the then graduate student Jocelyn Bell Burnell. And you can see that they're these little pulses that she had first discovered a little over 50 years ago. Here's another example of a very, very famous pulsar known as the Crab pulsar. So in the year 1054 AD, astronomers around the world saw a giant bright flash of light up in the sky. And that was associated with a supernova explosion. They didn't know at the time. It was so bright that it looked like a star that was visible during the day. Like a star you would see at night. The sun is visible during the day. I know, I often get that. And in the center of which is a pulsar. And these blocks here are showing 1 millisecond snapshots. So you take a picture every millisecond, and you'll notice that there's an object between these two on the bottom right that comes and then disappears, and then shows up again, and then disappears. And the period of this pulsar spins every 33 milliseconds, and you're seeing both sides of the beam. You're seeing one beam pass you, and then you're seeing the other beam pass you, and then one again and the other again. Very, very, very repetitive, very, very, very stable. We can use these as clocks that have been given to us by nature. And these are clocks that are as good as atomic clocks up in the sky. Okay? So the easiest part of my collaboration to figure out, which again, the North American Nanohertz Observatory for Gravitational Waves. So now you all know what a gravitational wave is. It's something that is changing the distances between us and space. 1 nanohertz is 1 over 30 years. So we're doing an experiment that is taking years and decades long. And North America is the easiest part of that name because we're situated in North America, and we use North American telescopes. So there's many of us in the US and Canada and really around the world. There are many scientists now. We use 4 telescopes, one of which sadly collapsed about 1.5 years ago. So that was the Arecibo telescope down in Puerto Rico, which was a 300-meter telescope, 3 football fields across. We spend a lot of our time at the Green Bank telescope in West Virginia, which is a 100-meter, fully steerable, fully tiltable dish. So imagine a football field that can rotate around and turn up and such. Okay, so we do a lot of observations there. We're also these days, in the last couple of years, observing with the Very Large Array, which is a set of these 27 dishes in this Y configuration in New Mexico. And we're also using these 4 half pipes called CHIME, which is up in British Columbia now. We use the largest radio telescopes in the world to observe our pulsars. And our pulsars are these tools which we are using to detect gravitational waves. And when we measure pulses, we get a whole sequence of them. Remember, some of them spin hundreds of times a second. And so we're trying to make a measurement. We can take lots and lots and lots of pulses. If I stare at it for 1 second, I will get hundreds and hundreds of these pulses. If I stare at it for 1 hour, I can get hundreds of thousands or millions of pulses. And the power of this technique called pulsar timing is that even though individual pulses, now this is real, these are real data, individual pulses all look kind of different, they average into an extremely stable shape. Imagine that the weather, each rotation, the weather is changing quite a lot, but the climate on these pulsars is extremely stable. And I will admit right now, nobody really knows why. You can test it and say, is it stable? Is it stable today? 10 years from now, we can go and test how stable it is, and it looks exactly the same. By some miracle of nature, they are extremely stable. That allows us to time tag exactly when a pulse arrives, making them an extremely good clock. We need to be able to time tag when a pulse arrives to well within 1,000th of the width of a pulse. So a pulse is traveling at us, may travel for thousands of years through space, and we need to be able to figure out when it arrives at our telescope. Some pretty crazy precision, which I will get into. But first, I want to impress upon you just how powerful these pulsars are as clocks. And so I've picked this one, which is one of our better pulsars. So I've cherry-picked it a bit, but all of the measurements you'll get are kind of comparable. This is one of the most precise measurements that you will ever see. And we have that in the middle of our data set, which happens to be some random day in 2011. I know exactly how fast this pulsar was spinning, 2.9 such and such milliseconds, plus or minus, there's a 9 over there, which is the error on that 7. Okay, that's one of the most precise measurements you'll ever see in physics, which is why I think this is so cool. And we also know that because pulsars are spinning and they're emitting this radiation, that radiation is leaving, it's energy that's leaving. And so the pulsars are slowing down over time. The period is changing and getting slightly longer and slightly longer. But we know what that is and how it's doing so. And so I know that the last digit, that 7, changes by 1 every 71 seconds. So every 71 seconds we go, that number ticks up, and it's getting slower and slower and slower. That means that if you work it out, that 0 there in the list changes every 226 years. And I know that really, really, really well. Okay. And on top of that, I know that from the middle of my data set to the start of this talk, so if we started exactly on time by atomic clock measurements, that these are the number 125 billion pulses, rotations have occurred between February 18, 2011 and October, I say 22nd because I'm using UTC here. That's how many pulses, that's how many rotations have occurred. I know that exactly, and I know that for all of the pulsars that I am observing. Okay, I think that is so cool. Another fun fact about this pulsar is just that it is actually in the most precisely measured circular orbit in the universe. Any circle, there's no better circle measured in the universe. It's orbiting around some companion. We don't quite know the orbit, we know the orbit pretty well. It's about 80% the size of the sun. So it's going around its companion very, very, very close in. But I know that the orbit is slightly eccentric. It's slightly an oval. The amount I know it's an oval by, the power of pulsar timing, is that the difference between one length of the orbit and the other length of the orbit is 3.5 micrometers. That's less than the width of a hair, okay? So I know from my measurements that some two objects are spinning around each other in just slightly off of a circle. This is the best measured circle in the universe. And we need the power of pulsar timing because the effects of gravitational waves are incredibly tiny. If you work out, given that the typical strengths of gravitational waves that we would expect, and I'm not going to justify that here, but we would expect something like this 10 to the minus 15 number. So 1 part in 10 to the 15 is how much distances are changing. You work that out, I need to be able to measure how distances are changing between a pulsar that might be thousands of light years away and us. I need to know how much that's changing by maybe 100 meters. Maybe something a little bit like the size of this building or a little bit less. If I turn that into a time, how precisely do I have to measure arrival times at my telescope? That's something like 100-ish nanoseconds. So a pulse leaves this pulsar, travels through space for thousands of years, reaches us here at the Earth, and I need to be able to predict when it arrives to within about 100 nanoseconds. Not only do I need to be able to do that, but we can do that for many, many, many of our pulsars, which means that we can detect, hopefully, gravitational waves. Okay, and this is a pretty complicated process, as you can imagine, so I'm going to walk you through it just somewhat pictorially. In a perfect universe for a pulsar timer, the universe would look something like this, where you have a pulsar at one end and you have your radio telescope at another, and pulses are just coming at you very regularly, and life would be good. That would be extremely easy to measure. And of course, that's not what we get. The telescope is not floating in space. It's on the Earth, and the Earth is rotating around, and the Earth is going around the sun. It takes 8 1/3 minutes for light to reach the sun to Earth. That means that the light travel time across the orbit is over 16 minutes, 17 minutes. So I need to be able to know where my telescope is in the solar system really, really precisely in order to measure to 100 nanoseconds. On top of that, most of our pulsars themselves are in binary systems. And the problem there is that I can't go to those binaries to measure them. I can go to other planets in our solar system and measure the masses of the planets, measure the positions. I can't go to those systems. I have to just infer what those are from our measurements. The arrows are representing the fact that that pulsar binary system and us are not stationary with respect to one another. They're moving through the galaxy, however they happen to be moving. We have to be able to measure that. One complicated, obnoxious effect is that space itself is not a perfect vacuum. It's not empty. It's full of stuff, and that stuff actually causes your light to break up, just like if it was going through a prism. You send white light through a prism, you get blue light, you get red light, and both of those take longer or shorter amounts of time to reach your telescope. So if I need to be able to know exactly what rotation of the pulsar I'm on, so I can use it as a clock, that answer changes whether I'm looking at redder light or bluer light. So I need to be able to pull that all together. And on top of that, for 80 different pulsars, that's how many we're observing right now, all of which are in different binary systems. They're all moving through the galaxy differently. The stuff in between us and the pulsars is all different. On top of that is the very small effect of gravitational waves, which is causing the arrival times of pulses to change ever so slightly. Okay, so this is an incredibly difficult experiment. But that's what science is. It's a whole bunch of very difficult experiments. If it was easy, it would have been done before. And the power of pulsar timing really comes in when we have a model, a predictive model that says we have some data, you have some data in the gray, And this model over here is bad. My lines don't match up with what my data show. And this one down here is good, where my black lines do match up with what I am measuring in the data. Okay, so I need to have a good timing model that takes into account what the binary motion of the pulsar is, what the spin period of the pulsar is, how it's moving through the galaxy. And we've gotten very good at this over many, many, many decades. So we're pretty good at understanding all of these different effects. Okay. If I look at, and I take a graph of my data, my observations of the arrival times, and I subtract from that my expectation, my model, I get the graph of what's called residuals. And if my data matched my model, then data minus model would equal 0. My data was exactly my model, data minus model would equal 0. And all of these residuals would be right on this 0 line here. Okay. Any deviations from the 0 line mean that I'm seeing pulses arrive early or late from what I expect. And some of that is bad because that's things that I might not understand. For example, if I have something wrong, I don't understand something about the pulsar system that I'm measuring. But some of this is good. In here are the imprints of gravitational waves, right? The differences, the distortions of space that cause these pulses to arrive early or late. That's what it is we're looking at. When we look at 80 different lines of sight, 80 different pulsars, we're coming up with these really complicated models and then looking and seeing what is left over. And can we understand between the different pulsars what is left over? Gravitational waves will look differently in these plots of residuals. So if, for example, we had a single binary system that was emitting gravitational waves, and I haven't talked about what the sources are of our gravitational waves yet, I'll get to that shortly at the end. Gravitational waves might cause pulses to arrive early and then late, and then early and then late, and so look like this sinusoidal pattern. So we can look for sinusoidal patterns in our data, and we do that. If you add up lots of these sinusoids of all different amplitudes and all different wavelengths, you might get something that looks more like this random walk. And that's from what's called the stochastic background. If instead of one binary system, there's lots and lots and lots of binaries through the universe, they're all producing waves that are coming to us. And what we would expect to see and what we think we will see first is, in fact, something like that red line, some kind of a random walk. And really the smoking gun in all of this is if we can see what's called the angular correlation pattern. That is, imagine I had 10 pulsars all in the same direction of the sky. And let's say that space expands between the Earth and all of those pulsars. All of those pulses will all arrive late. Even though the pulsars don't know anything about each other, because space is stretched between us and those pulsars, all of the pulses will arrive late. And if space compresses, all of the pulses will arrive early. So they're correlated. And if instead of their separations between the pulsars being 0 degrees as we see them, you can imagine if there's 10 degrees separated, they're probably still pretty correlated, just slightly less correlated. And if they're 20 degrees separated, they might be slightly less correlated. And due to complicated reasons of general relativity, if I plot the angle between the pulsars on this axis, so from 0 to 180 degrees, this is what the correlation should look like. And nothing can produce this correlation, which is called the Hellings and Downs correlation after Hellings and Downs. Nothing else we know of can produce this pattern, only from gravitational waves. So that's the smoking gun of what it is we're trying to observe. Trying to take our 80 pulsars, look at the correlations between all of them, and try to see if we can pull out this Hellings and Downs curve. And so we're observing 80 pulsars. That makes up a pulsar timing array. So there's an array of pulsars that we are timing. And it really is building a detector for gravitational waves that is the size of the galaxy. So LIGO was a detector that's about 4 kilometers long, and there's 2 of them. There's one in Louisiana, there's one in Washington State. Our pulsars are distributed across the galaxy. So our detector of gravitational waves is a galactic scale detector. Here are all of the pulsars on this map of the sky. The Milky Way is in the gray line, and for various reasons, we observe lots of pulsars over here. That's just where we happen to have found many of them based on the surveys that were done. If I draw them instead on a schematic map of the Milky Way, here are a bunch of the spiral arms, you can see that our pulsars make up a decent fraction. They are many, many, many hundreds or thousands of light years away from us. So our detector really is a good fraction of the size of the galaxy. And as we find new pulsars, we continue to add them. We do perform more surveys. We find pulsars that are farther and farther out. We're continuing to add more and more and more to our array. And the ultimate goal is not quite to just say, yay, we've detected low frequency gravitational waves and we've done our job. We're trying to build a detector that opens up new astrophysics and a new window to the universe, right? Every time we open up one of these wavelength ranges, we learn new things. And the primary thing that we want to study with our nanohertz gravitational waves are how galaxies merge over the lifetime of the universe. And the reason we want to study that is that we see, you can go out with backyard telescopes, and you can see galaxies merging. We see lots and lots and lots of these galaxies merging. In about 4 billion years, Andromeda will merge with us, the Milky Way galaxy. Okay, so if you wait around, you will see that happen. And we see the merger processes get closer and closer when we look at different sets of galaxies. Each galaxy has a supermassive black hole at the center. By supermassive, our Milky Way has one that is a mere 4 million times the mass of the sun. There are some that are 10 billion times the mass of the sun. They really are supermassive. Every galaxy has a supermassive black hole in the center, and we see galaxies merge. Therefore, we should have that as the 2 galaxies merge, the 2 supermassive black holes should merge. Those 2 supermassive black holes, when they're in a binary and they're merging around, they are producing gravitational waves. So they're like the gravitational waves that LIGO has observed, where you take 2 stellar mass black holes and you have them merge around. The only difference is that the source of them isn't these stellar mass black holes, it is these supermassive black holes. And it takes longer for them to orbit around, and so the periods of those gravitational waves are longer. Okay, so the astrophysics, the underlying stuff that we want to study with our detector are primarily these supermassive black holes. Okay, this is from our latest data release that came out in 2020, and we're working hard on our current data release. So we have not detected low frequency gravitational waves, I'm sorry to say, but I want to convince you in this slide that we think we're pretty close. Okay, and here's why. Because if you go to a casino and you're a betting person, then maybe you'll take these odds. So we came up and we did our analysis and we tried to see if we could find the Hellings and Downs curve. We didn't really. It's maybe there if you squint, it's kind of hard. You know, maybe there's a Hellings and Downs curve in all of these points, but it's pretty difficult. What we did discover was that you can place some betting odds and say, what is the probability or what are the odds that there is a common signature, some kind of common wiggliness in all of our pulsars? And it was quite significant. It's about a 10,000 to 1 bet that that's the case. That's a pretty good bet. Okay, so we see this kind of wiggly pattern in the residuals of our pulsars, of all of our pulsars. What we don't have yet is a strong enough bet of the Hellings and Downs curve. I only have 2 to 1 odds, which is not enough for me to bet my career on, and nobody else in my collaboration is about to bet our career on. Okay, so we're in kind of a unique holding pattern where we see in our pulsars what we would expect from gravitational waves. They're all doing this wiggly pattern. in the residuals. They all look consistent between all of the different pulsars, but we don't yet have that last piece. We don't yet have the smoking gun of the Helmings-Downs curve, so we haven't yet been able to claim a detection of gravitational waves, unfortunately. We are working extremely hard, as you can imagine, on our next data set. We are hoping to announce those results early in spring, so stay tuned for what the results will be from that analysis. And so I'm hoping I've convinced you tonight about what gravitational waves are, why we want to observe them in general, why my collaboration wants to observe them in general, and we really are opening up a new window to the universe. So LIGO and Virgo, they have really successfully in the last 7 years just expanded the amount of our knowledge of the universe by their gravitational wave measurements. And we're really hoping that in the next year or two, we're going to add pulsar timing arrays to this and open up yet another window to the universe. Thank you very much for your attention. I will happily take questions. Yes, please.
What's making your measurements better as time goes on? Is it the fact that you're adding pilot measurements, that timing down is better, or are measurements getting better?
Yes to all of the above. So we're just observing for longer. That adds just more signal. There's more chance for us to get the wiggliness. We're observing more pulsars. So when we first started in 5 years, actually I have my extra slide. Our 5-year data set had 17 pulsars. And as we've observed longer and longer and longer, just the number of observations, each one of these dots is an observation that we've made of a pulsar. Okay. And so over time, we've just observed many, 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 many more. So that helps as well. The techniques have gotten better. So we've gotten better at improving cleaning our data, for example, for cell phone signals or satellite signals and things like that. One thing that's not shown here is that the instrumentation at the telescopes have improved. So we've basically gotten better receivers that we stick on the telescopes and they can collect more radio waves. That gives us a better signal. So all of these things have just really tremendously helped us. And it means that even if we add maybe a year or two worth of data, you might think, well, that's not actually that much. It's actually quite a lot because of all of the different reasons that I've given. Yeah, absolutely. Yes, please.
Thank you for a wonderful talk. Because you're doing these very precise periods of time.
Great question. So those are many things that LIGO has to take care of, because those, if you have a vibration that happens many times a second, that matches the frequency of gravitational waves that they are trying to observe. So for them, those are a problem. For us, it's a little bit less of a problem. However, for example, if you have an earthquake and it slightly shifts the position of where your telescope is or where the bedrock has settled your telescope. Fun fact for everybody in the audience is that light travels in 1 nanosecond about 1 foot. Okay, so if you're trying to measure something to 100 nanoseconds or less, let's say 10 nanoseconds, that's 10 feet. That's twice my height. So if things settle and the position of your telescope moves ever so slightly because of whatever one of these reasons, we actually do need to know about it. And it comes down to very bizarre things like at the Green Bank telescope, it sits on a track and there's thermal expansion of that track. Now, will it make a difference of 10 feet? Probably not. May it make a difference of a foot or two? Yeah, it could, right? All of these things can add together. So we do actually have to take into account a lot of these effects over time. When before Arecibo collapsed, it was hit by both a hurricane, but also an earthquake. That earthquake, we weren't quite sure what the end result was of where the dish sits, where the actual receiver, I should say, sits in the grand scheme of our entire solar system, right? So you have to take those things into account and actually check that that's the case. Yeah. Yes, please. Oh, absolutely. You can see it over the course of like one night. It's so precise, yeah, that over the course of a night, you can see that it could drift slightly. Yeah. That just goes, that's not a statement of them changing very quickly. They change very slowly, as I showed. It's that we can measure them so well that you can actually see it drift in our data. Usually over the course of weeks, though, when they're first detected, and then you try to figure that out, it takes a few weeks, and you say, I know exactly how it's slowing down over time. Yes, please.
So is our solar through space relative to the rest of the galaxy?
Yes, that is built in. The way that we in astronomy worry about it is that we just pretend sort of that the solar system is fixed, and then we say, how is everything moving with respect to us? And that makes it kind of easy, or easier at least. Technically, that is correct, that we are both moving, but it turns out that you can kind of remove that. Yeah. Yes, please. Yes, it's an extremely complicated process. We try to time tag to GPS, so we need to have some receiver, some reference clock here on the Earth. Otherwise, you can make a measurement and say, what time did that happen? I don't know. Yeah, so we time tag it to GPS. In order to make this work more precisely at the observatories, we use what's called a hydrogen maser. It's kind of like a laser-ish, but emission bouncing back and forth due to hydrogen. And that is a very stable clock over very short time scales. So you're able to say, during this observation, I am really, really able to time tag when my pulse arrives. Then we take all of our measurements over 15 years and are able to correlate that. There are some questions about, for example, how well we do versus the atomic clock standards. It is very possible, and we are noticing this now as my collaboration and I have talked about it, that atomic clocks are saying one thing, pulsars are saying something that's slightly different over a long period of time. And one problem is who is right? And maybe neither of them are right? They're just the best that we can possibly do. So we're really trying to grapple these questions, because when you get down to 10 nanoseconds, these things really matter. Yeah. Yes, please. Yes. That's a great question. So for us right now, for single sources, it sort of depends on which direction you're looking in the sky. The reason it depends on that is because we have many more pulsars on this side of the sky than on this side of the sky. So we're more sensitive this way, and whatever happens to be this way. The answer is, in this direction, it's a few 100 million light years that we can observe things. For reference, the Andromeda galaxy, which is the closest nearby large galaxy, is a little less than 1 million light years. So many, many, many galaxies distant that we can observe. We can observe some of the nearest clusters of galaxies where lots of mergers are happening. And we've actually, even though we haven't detected anything, we've been able to make statements. So for example, that in the nearby Virgo cluster, there are no supermassive black hole binaries with a mass of 1 billion solar masses. And that's interesting because we know that there are individual black holes out there with masses of 10 billion out there. So it's not that we're making these constraints because we haven't detected anything yet, but they're actually astrophysically meaningful in that regard. So a few 100 million light years in sort of this direction, and maybe, let's say, I don't know, 30 to 50 in sort of this direction right now. And over time, as we observe more, we get farther and farther out, just like LIGO does. Yes. Was there another question? Questions online? Okay, maybe I should be checking here. Sure. Nope. Stunned silence. Everyone's asleep online. Yes, please. Well, I know for a fact that one of the pulsars, the periods, there's little tick marks that tell you what the periods of these pulsars are in this pulsar map. I know one of them is actually wrong because later on it was measured better, and then what was engraved on Voyager was wrong. So don't ask me which one that is. I have no clue. That's a good question. I actually don't know how those pulsars, among others, were chosen. I would probably first look at that. The pulsars that I tend to think, they're like my children, so they all have their unique, weird characteristics, of course, because this one is odd in this way and this one's odd in the other way. So I would pick them for various unique reasons that probably aliens don't care about whatsoever and think, why the heck did you choose these? I have no clue how that's a great question, how the Voyager ones were originally chosen. I just do not know. Please. Mm-hmm. Yeah, that is a great question. For the Earth, those things probably aren't a big deal. Actually, a lot of that gets absorbed into the GPS timescale. So you may have heard in the news recently, or not, there was maybe a month or two ago, this idea that we should add what's called negative leap second. So it turns out that if you didn't realize, if you may hear in the news every now and then, that we add a leap second to GPS because it links to what the Earth's rotation is doing, and it slows down over time. And what was concerning is that nobody knows why, but suddenly it was speeding up slightly, the Earth. So all of those effects on the Earth are kind of absorbed into that timing. And then so yes, things change, but then you kind of just add a leap second and you say, oh, okay, we're all good. There are plenty of longer term changes. And so we work with, for example, folks at Jet Propulsion Labs. They work on understanding where the Earth is in the solar system because of gravitational pulls from everything. Their concern is they want to be able to shoot a probe and land it on an exact spot on Mars. So they need to know where the Earth is in the Mars, and Mars is really, really, really precisely. What we care about is where the telescope is in the solar system. And so there's actually some weird things that come into play. So there's many asteroids that you think would have the tiniest pull on the Earth, and they do. But when you're trying to measure to 10 nanosecond precision, you need to actually be able to figure those things out. Juno, which is a mission that's orbiting around Jupiter right now, has refined the mass measurement of Jupiter, and that tells us how, even more precisely, how Jupiter is pulling on the Earth, how Jupiter is pulling on Neptune, which is pulling on the Earth, all of these kind of crazy things. And so really it's the positions of planets and asteroids that affect us more on the longer terms. But we think at this point we know it pretty well. We know it pretty well now. Actually, we had to talk to the folks at JPL, Jet Propulsion Labs, with two of our data sets ago, because we came to them very concerned where we said, depending on which version of your model of the solar system we use, we get different answers, and that's a problem. And so we knew back then the position of the Earth, or really it's the position of the center of mass of the solar system, but you can translate that to the position of the Earth. We knew it back then to about 200 meters, which is pretty good if you think about it, but not good enough for what we needed it to. We know it now to about 10 meters or so. So something like, we know where the Earth is in the solar system to the size of this room, which is absolutely remarkable.
So pulsar measurements have helped.
Yes. Yeah. Well, we intentionally, it's not that we don't give them our measurements. We say, please don't use our measurements, but we use it as a check outside of it. So they do everything independently. We're doing everything independently, just so that neither of us get totally screwed up is the goal in all of this. Thank you very much.